Howdy everyone, and welcome to our first video lesson for Geometry Proper. Welcome, welcome, welcome. So today we're going to jump into inductive reasoning. Specifically, that is, we're going to talk about patterns and solving problems with patterns. So here you can see the very first page of our overview of geometry. We're going to walk through this together, okay, pretty quickly. So let's jump right into it. We have learned how to use algebraic functions to describe various situations, okay? So in the past, in middle school, you probably dabbled in algebra, using some algebra to solve problems. Now we're going to use those same skills, but for geometry instead of algebra. So if you remember, geometry is about spatial reasoning, about spatial senses, right? About objects and their positions and relations to each other. So one of the big things we're going to talk about is the shape and size of objects around us, and specifically relationships between shapes and how they connect together. So mathematicians, one of the foremost things in mathematics is problem solving through patterns, making predictions. In fact, most sciences are about predictions. So looking at these images, we can see various patterns in these things, right? How are these patterns made? Where do they come from? Let's talk about some of the patterns you can see in nature to prepare us for some of the patterns we'll talk about together as a class. So a nautilus seashell is a spiral pattern that we call the golden spiral. This is because it's based off of something called the golden ratio. So this spiral you can see makes a really pleasing shape. There's different ways to make spirals. Why does it move in this specific pattern, right? Why is it that it gets tighter and tighter in this specific way? It's because it's an example of the golden rectangle. The golden rectangle is another form of the golden ratio. So this is a rectangle with dimensions that can be divided into a square and a smaller rectangle. So you can see every time we build another rectangle off of this one, they have a certain pleasing way of almost like not quite doubling in size, you can see, but building off the other one, where one side is a rectangle and the other side is this square. And if they keep going and going, let's see, and go a little faster, right? Look at that. Pretty cool, right? This is the same pattern that a piece of paper has, actually. A printer paper also shares this pattern. That way, when you make different proportions of paper sizes, they'll have that pleasing connection to each other. Now, what about a head of broccoli? What's special about this? Well, if you notice, what we have here, the stem of the broccoli, right, compared to the florets, the little trees, essentially, if you pull away that little floret, it actually looks like you got another piece of broccoli, right? And then those florets also break into little pieces too. Let me show that off real quick. Right here, right? This almost looks like another miniature floret. And then inside those, there's other miniature florets. This is what we would call self-similarity. Self-similarity is very important in mathematics. The idea that future parts of the pattern are building off of previous parts of the pattern, right? It's like the pattern is nested inside itself. So here's another example of self-similarity called the Sierpinski triangle, a very famous triangle that you can find in mosaics and tile work and architecture all throughout the world. What we're doing here is, well, I won't describe the pattern. What are we doing there, right? Each of these smaller triangles is formed similarly to the large triangle, right? They're built inside it, but what's the pattern that they use to make it, right? What's the process? One of the most famous patterns in mathematics is what's called the Fibonacci sequence, described by Leonardo Fibonacci. So here you can see the branches of trees developing over the years follow this pattern of the Fibonacci sequence. If you'd like, pause the video right here and try to predict if this is the first 6 years, how many branches do you think will be in the 7th year? How many branches do you think will be in the 8th year, right? So pause the video, consider that. What's going to come next? You might have seen the Fibonacci sequence before. What do we think? Well, what I'm seeing here, right, is that 1, 1, 2, okay, so it's something to do with these ones, maybe, so it's adding 1, but it didn't add 1 the first time, so plus 0, plus 1, plus 1, okay, so 0, 1, 1, then 2, then 3, then 5. Well, that's the self-similarity, right? That's the first 5 numbers of the sequence. So if it's self-similarity, plus 1, plus 1, plus 2, plus 3, plus 5, plus 8, right? So it's going to be 21. And then this one's going to be plus 13, so that's 34. And then this one's going to be plus 21. Ooh, so that's 55, right? So what we found is that self-similarity. In a different way, it's not a shape we're seeing necessarily, but when something's building off of the amounts of previous parts of the sequence, right? Like how the branches branch based on the previous branches, that's going to make something like the Fibonacci sequence. And you can see it here with when we have a pine cone, the number of these little splits is based on the splits on the previous level, right? And with a sunflower, same thing. It's based on how many spaces were left by the previous row or circle, I guess. So the process of observing patterns and forming conclusions about those patterns is called inductive reasoning. When you observed the branching pattern and filled in the sequence of Fibonacci numbers, you were using inductive reasoning. And whether you've known it or not, you use it all the time, okay? So Sherlock Holmes is famous for his powers of deduction, right? He sees some examples of things in the world around him and he reaches a conclusion based off that. That's actually induction. It's not deduction. What he's doing is the power of induction, right? Observing patterns, observing evidence and going, I predict that the murderer was blank, right? Likewise, when you have previously burned yourself on hot things, you know to use oven mitts in the future. When you see rain, you know that you need an umbrella. And in the case of science, we will try to make experiments and then predict general principles based off of those experiments, okay? So when we're doing this, we're gonna see specific examples and make a prediction based off of those. Allow me to add our own little shorter and simpler definition right here, okay? So what I'm gonna say is, and I'll just make it pretty big. I liked the process of observing patterns and forming conclusions, but I'm going to say inductive reasoning is reaching a conjecture based off of our observations. What is a conjecture? Well, a conjecture, we can just replace that, right? A conjecture is a prediction, right? So it's not perfect. We don't know it's necessarily going to be true, but we can guess, right? We can say it's probably going to be true. It's probably based off of what we've seen. And you do this all the time without even knowing it. So today in class, I want you to just briefly review this video if you need to. Be ready to talk about patterns and predictions, okay? And in addition, I have your Bayway trait of the week posted again as well as a Padlet. So on the canvas, you can see this Padlet. Please complete it before class. It is about problem solving and perseverance through problem solving. And as well, we also have a IXL assignment. I will be signing that at the end of class, but if you want to look over the instructions and be ready with any questions you might have about the assignment at the end of class, go right ahead, okay? You got the time before class to do that. All right, I look forward to seeing you all very soon. Have a good day.